This is what we're going to cover. Understanding, and a lot of you, I'm sure, have a basic understanding, so that'll be a brief explanation. Recent changes to the CSA Z462 standard. That was released in January this year, and what's some of the new items that apply to arc flash in there. Methodologies to reduce risk, and I'll talk a little bit more about risk later on in the presentation, but what CSA wants to do in the Z462 standard is make sure people understand what they're talking about with regards to risk and risk assessment. So that'll become a little clearer maybe by the end of this presentation. And the last one is mitigating the hazard itself. Can we make it smaller? Can we get it lower? That's the issue. So if you remove the electricity from a workplace, there is no electrical hazard. That's more or less an understood thing. If there's no electricity there, then you don't have a hazard. And there's a step-by-step procedure. More or less, we use the word lockout tagout in a lot of cases to get to what's called an electrically safe work condition. You know, open the circuit up, make sure your lock's on correctly, make sure there's no voltage there. You know how to use your voltage tester, and then if you need to, you put on temporary grounding. Here in Ontario, we've got Occupational Health and Safety Act and the Occupational Safety Act and its regulations. And there are 3 regulations where this specific phrase 42.1 appears. It may not be the same number in construction and healthcare regulations, but in industrial establishments regulations, which would generally apply to this facility right here. If the electricity, somebody was working on the electrical system and it's their workplace, then this would apply. The worker shall use the rubber gloves, mats, shields, and other protective equipment and procedures adequate to ensure protection from electrical shock and burns while performing the work. The word burns is in there, shock is in there, and this has been around since the mid-1970s. It's not a new requirement by the Government of Ontario to protect workers in the workplace for shock and burns, or we could also say arc flash in there, while they're doing the work. So it's not a new regulation. It's just that we've got some new ideas on how to deal with arc flash, how to calculate it, how to know what personal protective equipment to wear. And if we're dealing with shock, it's a fairly straightforward thing. Do you have enough insulation, and are you far enough away from the hazard? Using distance and rubber, basically, rubber gloves on our hands, good rubber on our feet, hard hats with insulation capabilities, sticks when we get above 1,000 volts called hot sticks or grip balls or live line tools. We have the tools to do shock fairly easily. And this is an example just showing some rubber gloves and leather protectors. And still to this day, last year we had one of our field service persons tell us they were out at a customer site in the Toronto area and they were putting the rubber gloves over top of the leather gloves. Opposite to what you should be doing, but that's an unusual case. People just didn't know. You got 2 pairs of gloves, which way do we put them on? They had the wrong way. Didn't have the rubber on the inside. So rubber gloves are easy. You pick the right glove class, you put them together correctly, you send them off to get them tested every so often. More or less that's it. Plus certainly you don't want to be doing anything around live equipment if you don't know what you're doing. You need to be a qualified person to be doing work on live equipment. When it comes to the arc flash hazards, it's another story in terms of how complex it is to figure out what this hazard is. And the best practice guide in Canada for electrical safety in the workplace, this one called CSA Z462, is the one that's giving a lot of guidance as to what should we do about this safety issue called arc flash. So on this slide, it's a definition. What is the definition of the hazard? It's a dangerous condition associated with a release of energy caused by an electric arc. Well, that release of energy can be light energy, heat energy, pressure wave, shrapnel, molten metal, toxic gas. There's a whole range of things that are nasty things that are coming out of an arc flash. What we're dealing with for analysis and PPE and labeling so far is just the heat hazard. We're not dealing with the pressure wave, other than we want you to wear ear protection for the pressure wave. We want you to wear safety glasses in case there's some shrapnel coming at your eyes. So there are some mechanical PPE required for arc flash, but the majority of it is how much heat is coming at the human skin. What's the arc burn hazard? In the 2008 standard, SED 462, there was a note attached to this definition that said that the arc flash hazard might be present if you're just interacting with the equipment. You're just opening a door or you're just turning something on or off. Possibly that arc flash could exist. And that caused a lot of, let's say, discussion with regards to, all, does it exist or does it not exist? And there is no easy button, there is no black and white answer. What happened after 2008 was, in the United States, the companion group, the National Fire Protection Association, and their 70E is equivalent to the Canadian ZED 462. They made this suggestion that if you do operate a circuit breaker, open or close it, and the equipment is properly installed, in this case according to the National Electric Code, which would be the companion Canadian code in this country, you've maintained it adequately, that's a very large wild card, and you operate it normally, you're not doing something unusual, then the chance of an arc flash occurring, opening or closing a circuit breaker, is remote. They would never say it's non-existent or there's zero chance. They'll just say it's pretty low chance. So that has come out recently. So to protect ourselves as humans for the arc flash condition, it gets down to that bottom right-hand corner. That's the temperature that's coming at us. And the top numbers, the 205 degrees Fahrenheit, is more or less where we're in trouble. As humans, we're in trouble at 205, and you could convert that to Celsius if you wanted to. But there's a big mismatch between what's coming from the arc in terms of temperature and what we're capable of accepting as humans. And somewhere in the middle, there's clothing that's catching on fire and burning and igniting, and the temperatures associated with that on this chart. What's been decided in best practice is protect humans from second-degree burns in the workplace. So the protection that is provided for arc flash is intended to provide protection against a second-degree burn. And the hands on the right-hand side are just showing as the degree of the burn gets worse and worse, we go from first to second and then to third, and there's even a fourth-degree burn. So the unit of energy that was chosen to describe the arc flash hazard is a calorie, and we put calories over a square centimeter of surface area to get our limit. And the top line is talking about the definition of a calorie. If you were in the science lab and you wanted to figure out how many calories it takes to raise, how much energy to raise 1 gram of water 1 degree C, it would be 1 calorie. If you were doing a movie, let's say on YouTube, and you wanted to be funny about it, you could hold your finger over a lighter for 1 second and say, yeah, I got 1 calorie of energy coming at me. But at the bottom, the known limit of human skin is 1.2 calories per centimeter squared for a duration time, an exposure time of 1 second. That's enough energy to get a second-degree burn on human skin. So that's a limit known. What's coming at us from an arc in terms of heat energy is dependent on 3 things. How powerful is the arc? And power in the electrical world is voltage times current, volts times amps, at the arc location. How close is the worker to the action where the arc's occurring? And that's worker distance, and we can work on that one later on in this presentation. And the last one is how long is the exposure? So getting a brief exposure may not be as bad as a long duration exposure. And certainly in the standards, the calculation standards, they talk about a person jumping out of the way in 2 seconds. Now, whether or not that could be done is sort of a judgment call, but we use time in that fashion. So it's power, distance, and time are the big components of arc flash calculations. There's been formulas written. This one has been around since the early 1980s, called the Lee formula, describing how energy is related to voltage, amps, time, and distance. So there's a formula that's available to do the calculations. And that formula calculates out an arc flash boundary. If I were to go back to this formula, and if distance was unknown, we left that as the unknown variable and plugged in all the other variables, volts, amps, and time, and then said, make that equal to 1.2 calories, we could get what's called the arc flash boundary. And they used to say arc flash protection boundary, but that word protection has been taken out in the last version of the Canadian Best Practice Guide, the Z462 standard. That's the bottom paragraph. So the concern is, do you get yourself into trouble, or have you crossed the arc flash boundary? That's the moment at which you kick in the arc flash hazard. If you stay outside the arc flash boundary, technically you will not get a second-degree burn should an arc flash occur. You might get a first-degree burn. There may be shrapnel coming at you and molten metal, but we're most concerned at this point with heat energy causing a second-degree burn. If you stay outside of that boundary, you should not get a second-degree burn. If you cross that boundary, then you need to wear appropriate personal protective equipment to protect you against the second-degree burn. And that gets back to the government's regulation. If you're doing live work, protect yourself from shock and burns. The 2012 standard has come up with information with regards to direct current. There was no information in 2008 on how to calculate arc flash for DC. And so we've got new tables and new equations for calculating DC for situations like batteries, battery rooms. Nuclear power plants use a lot of DC for their backup power. So there's quite a number of locations that can now use the DC equation. So that's something new inside the Best Practice Guide. Here's an example of an arc flash label. We want to warn people there's a shock and arc flash hazard. We also want to tell them, what is it? What's the quantity of the hazard? And so that is now the way that our company, Eaton, is putting together an arc flash hazard label. There is no standard to say the label must look exactly like this. And there is certainly a way inside of our federal WMIS program. The labels all across Canada must be the same. A WMIS label is the same in PEI as it is in British Columbia. But in arc flash world, that's not the case. We have to show certain quantities and certain pieces of information, but how you present it is still an open for interpretation. Blast pressure coming from the arc flash is something that we know happens. There's explosions, and some of you have probably seen the Eaton products here that are called arc resistant, that contain the arc blast in the skin of the equipment, the front and the sides, and then exhaust it through a weak spot or a plenum to a place where it shouldn't harm anyone. Controlling this blast pressure it can be done, but it's difficult, and we have some products at Eaton that can do that, called arc-resistant gear. We're dealing with an expansion pressure that is huge. 67,000 times original volume is much greater than the expansion of water into steam. So there's a big pressure buildup that needs to be controlled if you want to develop arc-resistant equipment. So there is a concern as to when does this blast pressure become harmful to the point of we're really worried about it. And in the Best Practice Guide, since the year 2000, they've created a line in the sand at 40 calories per centimeter squared. So when the calculations are done and the energy level at the working distance gets above 40 calories, then there should be something else done. And in this example here, taken right out of the Z462 standard, that's the exact words. It just says, do something different, something other than normal about this situation. Inside the standard, there's a requirement to, this is the new standard in 2012, there's a requirement to do all of the following: calculate flash boundary, calculate energy coming at the worker's distance, and the worker distance is to face and chest, not to their hands. The exception to that, and then you would figure out your personal protective equipment based on those calculations. The exception to that is using a table, and the table method is permitted to be used in lieu of doing energy analysis calculations. And we get back to a lot of people are familiar with HRC, hazard risk categories, and those values are still available inside the 2012 best practice guide. They're only applicable if you use the table method, and that's the big key now in understanding the shift in thinking from reporting these values if you do energy analysis. So any of you that are doing energy analysis or getting arc flash analysis done should be aware that hazard risk categories cannot be used or should not be used when detailed analysis is done. It is still allowed if you're using the table method. So there has been a distinction, and the reason for that is there is no evaluation of risk when you're doing energy analysis. There is no analysis of risk. We're just calculating out the hazard based on the parameters, the voltage, the current, the distance, and the time. We're not evaluating the risk. You know, is it more risky to open up a bolted cover, or is it less risky, let's say, to open a hinge door? This is where risk analysis comes into the workplace. What am I doing? And is it more risky to do something? And that's built into this table method. So it's the only place where we can use the word HRC, because that includes the word risk. And more or less what I just said is described on this slide. Risks should be evaluated at the workplace. There are a lot of rules to using the table method. It is the easy button. You could look up a value in the table method and you've got your arc flash analysis done, but there are a lot of, not a lot, but about 3 or 4 restrictions that you can't use the table method if, and the main ones are they put parameters around short circuit level, they put parameters around fault clearing time from fuses and circuit breakers, and if you fall outside of those parameters, you can't use the table. And that's described in this slide. What the best practice guide is hoping people will do is use formulas and equations that were developed to use a calculation rather than the table method. And this slide is just showing what's called the arc in a box experiment that was done back in the year 2002 to determine arc flash energies coming from arcs off of a 3-phase system. So the round discs on the white tubes are calorimeters. They're measuring energy. And then inside that steel box, it may be difficult to see from the back, are 3 copper-clad steel conductors, and they would develop a 3-phase arc on those conductors at the tips and measure how much energy is coming from there. And that experiment was done about 300 times and came up with equations that are used now in the software for calculating arc flash hazard. It is the preferred method on both sides of the border based on the Z462 standard and the NFPA 70E standard, with the table method being the backup method, alternative. How to do an arc flash study is listed on this slide, more or less the basic points. The most time-consuming and hardest part is the first bullet point. What have we got to deal with? What is the lay of the land? What does our power system look like in terms of cable runs, size of conductors? How are they run in conduit or in a cable tray? Is there 2 per phase? Are they in a metal conduit or a non-metal conduit? That's the cable side, and then the rest of it deals with the other devices in the system, transformers and motors and generators and utility connections. All of that data has to be gathered along with the timing information. Circuit breakers and fuses. What type of circuit breaker and setting do we have in terms of time? What type of fuse and size of fuse do we have for the same thing, for timing? Once you gather all that information, you have to determine how do we run our system with the tie circuit breakers closed, with generators operating in parallel. What is our modes of operation? Then we determine our short circuit levels, called bolted fault. And bolted fault is the worst thing that can happen. If we bolt everything together and have 0 impedance at the fault location, we would get a bolted fault, the highest quantity of fault current. There's equations that calculate out arcing current from the bolted fault, which is a lower value. And from the arcing current, that's where we say, how long will it take the fuse or circuit breaker to trip with that much arcing current flowing through that device? We record system voltages and equipment classes, more or less for the gaps of the arc and the types of equipment, like motor control center, switchboard, etc. and that goes into the equation. We determine working distances. How close would the human be to the type of equipment? There's some standards given for that. More or less at 600 volts or below, we're generally seeing the distance of 18 inches used. That's arm's length at your side, typical working away. The arc flash hazard is right at my fingertips and is coming at my face and chest. That's 18 inches away. Once all of that's done, the calculations can proceed to determine energy and flash boundary. So bolted fault, we connect it all together. It's the worst condition. And this chart is just showing how the fault current changes to a lower value from bolted. So the bolted fault is always higher than arcing current, and as the voltage gets higher and higher, as you go farther down on the chart to higher and higher voltages, the difference between bolted and arcing becomes less significant. So it's a much more significant change at 208 volts compared to, let's say, 600 volts, and it's almost insignificant above 1,000 volts, the change to arcing current. And once we know arcing current, we can determine our protective device clearing time. And we use graphs called time current graphs from a coordination study. And you have to certainly have some idea of how these graphs work and why they're used, but that's the connection. We find arcing current, and then we go to our protection settings, our time current graph to determine the exposure time. Inside of the Canadian Electrical Code, there has been a rule, and the rule is 2-306, that's been around since the year 2006, requiring arc flash hazard warning labels on new installations after that 2006 code was published. And those warning labels, examples of them are shown at the bottom of this slide. It's just a straightforward warning, arc flash hazard. There is no more information other than that required on the Canadian Electrical Code rule. Inside of the best practice guide, there is more information on what the arc flash hazard label should include. And you have to pick one of these four. The one that's generally picked is the top one. Energy level, available incident energy, and corresponding working distance. So that's the one that makes most sense to most people, but the other ones can be used. Along with that, you have to put voltage level, the arc flash boundary, and when the hazard analysis was done. They've included a sort of an expiration in the best practice guides of 5 years. They were suggesting every 5 years you go back and look, does our study still make sense? Is it current? Once you know what the hazard is and you know what your working distance is, you can select your PPE. And there's always a caution that it's not like you're putting a Superman suit on. It's not going to protect against everything, but it's there to prevent bodily harm should an arc flash occur. And it doesn't protect against things like shrapnel in some cases. The cloth in arc-rated clothing is not ballistic material. You can get some Kevlar sewn into the material, but it doesn't protect against shrapnel and some of the other injuries that could occur. It's protecting against heat hazard at this point, in most cases. So the steps boil down to decide, do you want to do detailed analysis or use the table method? Once you do that, you select one or the other, do your analysis, put labels on the equipment, and from the labels you select your personal protective equipment. If you're using the table method, you can use the HRC, hazard risk categories. If you use detailed analysis, then you must go to a new table in the best practice guide. It's called Annex H. It's at the very bottom of this slide. There's a brand new table as of January this year that is supposed to be used for arc flash hazard analysis calculations. And on the next few pages, I guess I got one more to go here. It's just describing the fact that this table is supposed to be used. You cannot use hazard risk category anymore. And they break it down into three bins or three levels. Up to 1.2 calories, that's the level where human skin can take. We can take up to 1.2 calories and not get a second-degree burn. We can still wear flammable clothing. It's still allowed. Non-melting, natural fiber clothing, and that's generally cotton, wool, silk, hemp, bamboo, rayon. Those are natural fibers that will catch on fire when exposed to arc flash hazard. And the number where people generally say we're going to catch on fire is around 2 calories for, let's say, jean weight fabric. They've tested jeans, cotton jeans, 100%. That will ignite somewhere around 2 calories. So there's a fine line between catching on fire and not catching on fire when you're wearing non-melting natural fiber. The only other thing that's required is safety glasses and hearing protection. Protect the eyes from shrapnel, protect the ears from pressure wave. That's up to 1.2 calories. The next level that we're using in 2012 is between 1.2 and 12 calories, and there's a list of items that are mandatory. You must wear all of those items, and the big news this year is balaclava. It's shown at the very bottom of this table. Balaclava was the last piece of the puzzle to protect more or less the back of the head from an arc flash hazard. We were not providing any protection to the back of the head with a face shield, and now it's a face shield and a balaclava together. There's a little bit of information in the middle there on gloves, and there's some limit to how far you can go with leather gloves on their own. 8 calories is the limit, and after that you must use a rubber glove with a leather protector up to 12 calories, or alternatively an arc-rated glove. Above, so I'll go back to this one. At 1.2 to 12 calories, there's a requirement to wear arc-rated clothing. That's flame-resistant and then tested for its arc-rating capability. Above 12, we're into what we generally call the bomb suit or the moon suit, the monkey suit, whatever you want to call it. It's a lot of protection required when we're above 12 calories. It's fairly heavy, snowmobile suit type of look. To get arc-rated material, we first find out if it's flame-resistant material, and there's a test to prove whether it's flame-resistant. That's shown in this picture here. The material is lit on fire. It's then checked with a stopwatch to see how long it takes for it to snuff out the flame, and then they measure the char length, or how much disappeared, and if it passes certain criteria, it becomes a flame-resistant material. That's certainly fine for race car drivers, people that are putting out fires, firefighters, people that work in petrochemical plants where there's a fire hazard from fuel. But we want to take it to the next level. That's arc-rated. And arc-rated clothing is tested in under arc conditions to see how much is its protective value. And in the middle paragraph is the term ATPV, which stands for Arc Thermal Performance Value. That's the one that we generally see on the labels of arc-rated clothing. So that must match what's on the label, or exceed. This picture is just showing the after effects. This is taken on an office floor, a picture of 2 layers of clothing that protected an employee pretty well, not completely, but the big news here was this person more or less walked away from the incident. Their clothing did not catch on fire and continue to burn. It was arc-rated clothing. There was more of a hazard than what the clothing was capable of handling. This level of 2 layers of clothing was capable of about 20 calories. The exposure was 60 calories after the fact. They weren't aware it was that high, but fortunately this person received a knee burn and an ankle burn. It's not visible very well on this slide, but the clothing on the left was the inner clothing, the clothing on the right was the outer clothing, and it burnt through at the knee and the ankle. Other than that, the person came out of that one pretty unscathed. Inside of the best practice guide, there's requirements for worker training. This is something that's new in the 2012 edition. What was not clear in the first edition in 2008 was how often what was appropriate and how often that training needed to be done. So that's been cleaned up and made more clear in the 2012 edition. So 3 years has been given as a limit to retraining. If you want to minimize your risk around electrical equipment, you have to use proper tools and equipment. You have to have good qualifications or knowledge of the equipment and use the appropriate personal protective equipment. So it's knowledge of where are you working, what are you doing, and wearing the appropriate protection. This is a picture of a person at the line side of a main breaker. And then at the line side of the main breaker, the big hazard, the hazard is much higher there. So any service entrance equipment, generally that's the bad spot in the power system for arc flash hazard, because the reason for that is the currents are generally higher. It's coming from the main power transformer. The short circuit currents are fairly high. And the operating speed to get rid of the problem, the exposure time, is determined more or less by the fuse or circuit breaker on the primary side of that main transformer. So at the utility voltage side, that's what we're relying on to get rid of this problem. So working on the line side of a device or in the same cell as the line side connections is a place where the hazard is generally high. And as we move away from that, we start to get relief in faster and faster operating speeds, which allows us to wear less protection and makes it easier to do the job. When we look at solutions, how do we get the arc flash hazard lower? These are the 4 items that come up. If you go back to that equation, it's the power of the arc. How powerful is the arc? Well, if we can reduce the short circuit current, we could make the arc less powerful. And the problem with that approach is that it is difficult to reduce short circuit current. You'd have to introduce some impedance in the circuit, so higher impedance transformers, longer cable runs, or a more higher impedance in your circuitry. Either transformers or cables is where you introduce that. And even if you did introduce a lower current, what you're going to get as a problem is not faster operating speed for your protection, but slower. So you introduce less powerful arc, but it takes longer to get rid of it. And that's generally what happens with that solution. So it's generally bypassed. We don't use that one. Move the worker further away from the arc. Plenty of those solutions around. I'll go through a couple of those in a moment. So that's distance. Distance is your friend. Faster fault clearing time. Let's try and make the arc not persist. Let's get rid of it as fast as we can. So there's many techniques available for getting the speed faster. And the last one is just say, why are we doing it this way? Is there a better way to do it? And one technique that came up in our service organization was, rather than using measuring tape or measuring devices, let's use a laser light to do our measuring. So there's other things we can do out there. So I'm just going to go through a few of the solutions. One of them is move further away, and this is the chicken switch. Now, the chicken switch is not an Eaton product, but you could put a chicken switch on an Eaton product. It's generally intended to move about from one place to the other. It's magnetically held, and it just takes the place of a person's hand operating a switch handle. Rather than moving it from side to side with your hand, you put the chicken switch over the handle, and 20 feet back you do the same operation from a solenoid-operated, battery-powered device. So that's a very unique way of remotely switching, moving further back. There's remote racking, and here at the show you'll see. I don't know if this particular model is shown, the one in the front right, but the operator is further back, and they're operating or racking in and out of a cell with a device. So it's more or less a way to remove the human being for the task of cranking in or out. Using windows that are transparent to infrared radiation and not having to open doors and covers is a huge amount of increase in safety, reduction of risk. We've had a lot of stories over the last few years of people being injured opening up doors or covers, and one of the tasks that's out there that we do quite frequently is infrared scan. That we can't see through the steel door. We need to get that door open or that cover off to get access to those parts that are still energized, because we want to have them energized to pick up the hot spots. And so infrared, reducing risk with covers is a good idea. Certainly they have to be installed with the equipment off. This one is on display here at the show, arc flash reduction through a maintenance switch. And maintenance switch has now made its way into the best practice guide as a technique. That's the CSA Z462. The technology is pretty simple. It's more or less, why are we waiting for the circuit breaker to delay tripping if we're working on that particular section of the power system? Why don't we put in play, during our maintenance, fast tripping? So this is just a way to introduce temporary fast tripping with a switch, simple switch, a light indicating that it's been engaged, and all we're doing is adding or introducing a fast trip. And it's sort of interesting to note that digital technology, microprocessor technology, takes some time to figure it out. It usually takes about 3 cycles to get an instantaneous trip reaction in the microprocessor world. But the analog world is immediate. It's like a knee jerk. If they hit you on the knee with a hammer, your knee will move. And the same thing with analog. It works very quickly, and it is the fastest technology. So in the Eaton solution for maintenance switch, and we call that ARMS, Arc Flash Reduction Maintenance Switch, we reverted back to an analog tripping device to get the fastest response we could and put that onto a microprocessor device. Another way to get the harm, this is more containment of the harm. Let's make sure it doesn't come out at people. Let's put it to a place where it doesn't harm people. And this is a picture of an arc flash switchgear test, and I'm just going to switch to a video.
Okay.
I wanted to stop it here for a moment, but a successful test would mean that the harm was redirected to a plenum and generally goes outside the building. Wherever there's a crack or an opening or a gasket, they will put a piece of cotton on that spot, a little distance away from the equipment. If any of those cotton squares catch on fire during the test, then the equipment would not pass the test. And so it's an indication of whether or not any harm is coming through the skin to a place where workers would generally be, at the front of the equipment, and in some cases it's the sides of the equipment as well, and whether the equipment has a strong enough skin to successfully contain that pressure and move it to a safer location, move it to the plenum and out. For those of you that are doing power system designs, this one certainly makes a lot of sense for arc flash. Why do we want a very strong short circuit current for a phase to ground fault if we don't need solid grounding? And so rather than solidly grounding the main power transformer and distributing a 4th wire in our system, reduce that exposure for a line to ground fault that's high short circuit current, reduce that only to those places where we need the 4th wire. So when we have single phase loads, or let's say 347 volt lighting, we would put a smaller transformer in that location, solidly ground the neutral, run a 4th wire, and that system does have high short circuit currents. But for the rest of the power system that only needs 3-phase 3-wire, we put a resistor in the neutral of the transformer and restrict the current to something like 5 amps. Very low amount of current, very low spark, very minimal, not a concern for skin burns, other than your tip of your finger, I guess, if it was close to the arc. That's a home pulling the plug out of the wall socket when the iron is on type of arc. So this is good design, and it certainly increases system reliability as well. Eaton makes product changes. That one way to get the arc flash hazard down is to come up with new ideas, like why are we doing it the way we used to do it? And this is one example of a change in design for motor control centers, making it more or less 2 pieces with a crank. And the part on the right-hand side is those contacts are ganged together. They move together. All 3 contacts can move in or out or make connection with the main bars or be pulled away from the main bars with a crank handle. And then it's an option for the operator. Do you want to be a real cowboy or do you want to be a chicken? Because the chicken option is to put a motor and do the cranking and stand 20 feet back to do the operation, or you prefer, you could be standing right in front of that equipment with a crank and cranking it in or out mechanically. So the idea here is, why are we plugging in the whole box? So motor control center wrappers or buckets we plugged in the whole thing. We connected it all together in one shot, whereas this is a 2-stage approach, which improves on safety by design.